Good noon, distinguished guests, fellow researchers, and participants of 14th CSIA 2023. My name is Hafiz Bilal Ahmad, and I am representing Xidian University, China. It is a privilege to be part of this conference virtually. Today, I am excited to represent our paper titled Intrusion Detection System in a standalone 5G network using machine learning evaluation. I am eager to share with you the journey of this research, with the challenges we faced, the methodologies we employed, and the promising results we achieved. So without further ado, let's dive into the world of 5G network security and explore the potential of machine learning in safeguarding our digital future. So here are the contents of my presentation. The first one is abstract, then it comes to introduction, then followed by research objectives, research literature review, methodology, results, and conclusion. First one is abstract. Our study integrate software-defined networking, network function virtualization, and machine learning to address the unique challenges of 5G networks. We have applied various boosted machine learning models with a highlight on AdaBoost model, which achieved a remarkable 99% accuracy in identifying 5G slice type. So its introduction, the importance of 5G in the dynamic world of 5G. In the dynamic world of 5G network, where IoT and mission critical implications are prevalent, efficient and intelligent network management is vital. The groundbreaking technology is not just about speed, it's a gateway to ubiquitous connectivity, enabling a host for new technology. From IoT to smart cities, 5G is backbone that support these advanced applications. The next one is slice type prediction. A vital component of 5G security is its ability to predict and manage different network slices. The capability allows for customer security protocols tailored to each slice unique requirement, enhancing overall network protection. Why slice type prediction is important? It is because slice type prediction allows network operators to efficiently allocate resource and optimize the performance of their networks by predicting the type of network slice that is required for a given application or service. Our service network operators can ensure that the application or service receiving the resources it needs to perform optimally. And the third one in introduction is the role of machine learning in the 5G network. At the heart of this advancement lies machine learning. It is a key player in ensuring adaptive security measures and predictive analytics. And there are several machine learning models we have used in our paper. The first one is Extreme Gradient Boost, which is also called XGBoost, which is followed by AdaBoost classifier, which is also called Categorical Boosting Classifier. The next one is Gradient Boosting Classifier, which is followed by AdaBoost, AdaBoost, and Light Gradient Boosting and Hist Gradient Boost. Our research objective in this study, we set forth to explore and quantify the potential of machine learning in enhancing the operational efficiency and security of 5G network. Our research is structured around 4 pivotal objectives. The first one is utilizing the deep slice 5G dataset. This dataset provides a realistic simulation of 5G network traffic, which is essential for testing the performance of machine learning algorithms in a scenario that closely mimic real-world conditions. The second is predicting communication type. This involves analyzing network traffic data to determine the nature of communication based on factors like packet loss and delay budget ratio. The third one is comparison of several boosted machine learning model that is previously described, like Extreme Gradient Boosting, AdaBoost, and other models. The fourth one is comparison of different machine learning models. Improving operational efficiency of 5G networks. By implementing effective machine learning models, the study seeks to demonstrate how 5G networks can be managed more effectively, ensuring security while maintaining high performance and service quality. And here is our background study. In our background study, we review various studies on 5G network security and machine learning application, noticing the lack of real-world deployment, insights, and scalability challenge. Our study aims to fill these gaps. Some of the researchers, they work on deep reinforcement learning in network slicing. Some of the one, they work on AI on virtualized network, performance framework for AI in beyond 5G networks, 5G network architecture and computing, and applications in healthcare and monitoring. And some have also worked in pandemic control during COVID-19. And every researcher, they come with some limitations and outcomes, and they are described here. You can see. Now, let's move on our dataset description. In our study on intrusion detection system, we have utilized a comprehensive dataset that is instrumental in our analysis. Let me briefly describe the key features of this dataset. This dataset provides an in-depth look into 5G network traffic, offering realistic simulation necessary for our evaluation. This dataset we used comprises multiple features with 6 input and 1 output variable, each representing different scenario within the 5G network traffic. And here are the features. You can see use case type, LTE, UE category, technology supported, GBR, packet loss ratio, and packet delay budget. And there are also devices how we can use case types. They are using in gaming, healthcare industry, and other. And similarly, 5G using their division as LTE and 5G and technology supported. They are also working on IoT and FG and LTE. Now let's move on methodology. In our study, we have adopted a methodical approach to assess the application of machine learning in enhancing the efficiency of 5G network. Our methodology involves a lightweight test bed using container virtualization. In first step, we have collected the dataset. From Kaggle, and there are 6 features that we use from dataset. In the next phase, we move on to data preprocessing, and where we use different techniques for dimensional reduction and principal component analysis. And then we split our data into training and testing. And then we applied several boosted machine learning models like XGBoost, CatBoost, Hist Gradient Boost, Light Gradient Boost, AdaBoost. And we use several machine learning evaluation performance metrics to analyze our model performance. The first one in our models, the first one is XGBoost. XGBoost, a scalable implementation of gradient boosting decision trees. It optimizes loss based on the addition of new learners to minimize the loss, and its versatility is it's applicable to both regression and classification tasks. XG supports both parallel and continuous tree boosting. The next one is CatBoost architecture. CatBoost automates managing categorical feature. It groups feature based on success metrics, and its efficient decision trees use obvious decision trees for faster predictions. And its versatility is also used in regression and classifications task. And move to next. The next one is gradient boosting classifier. This is the basic diagram of gradient boosting classifier architecture. It combines weak learner to build a robust classifier. It is an iterative function gradient algorithm. The next one in our category is adaptive boosting classifier architecture. It's ensemble learning machine learning method. AdaBoost, which means adaptive boosting, is an algorithm that employs the boosting technique as part of an ensemble method for machine learning. The next one is Hist Gradient Boost, used for classification task. It is a gradient boosting algorithm that uses histograms to approximate the gradient of the loss function. And the last is the light gradient boosting classifier architecture. You can see the diagram of LGB classifier. Light gradient boosting classifier divides the tree at each leaf level as it expands. In order to maximize its data loss, it selects the leaf that is the most advantageous for the growth. And performance metrics, we have used several performance metrics to analyze the performance of our model. The first one is true positive rate. Next come to false positive rate, then it is followed by accuracy. The next one is micro average. The next one is weighted average. It's also called the last one is the ROC and AUC evaluation. Let's move on to the results and discussions. This is the ROC curve of XGB boost, extreme gradient boost. It gives the highest accuracy at class 4. It says in 93% accuracy, and its micro average is 88%, and macro average is 77%. And you can see, and you can see it's the green line. It's the area for the 0.93 for the area under the curve. It gave us 93% accuracy. The next one is RC curve for CAD boost models. It achieved 99% accuracy for class 0 and 1, achieved 100% accuracy for class 2, 3, and 4. Its micro average noted as 99%, and macro average is at 90%. And figures show visual representations illustrate gradient boost classifiers, strong accuracy for specific classes and overall averages. Its best performance gave 92% accuracy for class 3 and 4. Its micro average noted as 93% and macro average noted as 79%. The next one, visual representation, highlights AdaBoost accuracy for specific classes and overall averages. Its highest accuracy is 91% for class 4. Its micro average is 88% and macro average is 78%. And it's followed by LGB, light gradient boosting classifier. It gave us a highest accuracy 92% for class 2 and 3. Micro average is 93% and macro average is 79%. The last but not the least, ROC curve of Hist gradient boost classifier. You can see it gave the highest accuracy for class 4. As the green line, it showed the class 4 accuracy, and it gave us the micro average 88% and macro average is 75%. So the comparative analysis of our different machine learning models. So from here we can see CAD boost, it gave us the highest accuracy for 99% for class 0 and 1, and it's perfectly 100% accurate for class 2, 3, and 4. And its micro average is 99% and macro average is 90%. It is the best classifier model for this approach. So in the conclusion, 5G network demands and solution realigns our software-defined networking, network function virtualization, and machine learning for industry-specific needs. Machine learning addresses challenges like slice prediction, route optimization, and resource management. Next one is testbed protocol and dataset usage. Proposed lightweight testbed using container virtualization for 5G machine learning development using Kaggle's deep slice 5G dataset to predict user communication based on packet loss and delay budget. Third one and the final is machine learning models and performance. We have evaluated our machine learning models using different evaluation metrics like ROC and AUC curve, accuracy, true positive rate, false positive rate. And in the last future implementation, potential study we can implement our study in 6G network and real-time slicing prediction suggest for future research. Recognized limitation in computational complexity and result interpretability emphasized for practical deployment. Addressing computational complexities without compromising accuracy in boosting machine learning models. And in the last,